Hello everyone, my name is Sreedharan and I will be presenting our work TLdR, a method for generating policy summaries that use temporal abstraction. This is joint work with Professor Siddharth Srivastava and Professor Subbarao Kambhampati. For an agent to be truly successful in real world, they need to be capable of collaborating with humans in the loop. A prerequisite for such collaboration is the ability to effectively communicate their plans to the users in the loop. While this is already a hard task in deterministic setting, this problem becomes much more challenging when you add stochasticity into the mix. Because now the agent would need to communicate policies which could potentially contain a large number of contingencies. To get a sense of the problems involved, consider a simple travel planning scenario where you're asking an automated system to come up with a policy to get you to your flight from your home. This sample domain was coded up in a relatively small PPDTL problem that contained only 30 grounded propositional fluents and 27 grounded actions. When we gave this problem to a planner, this returned us a policy of this form, which contained nearly 100 reachable states from the initial state. Now, dumping this policy would be if we dump this policy to a user, it would be nearly incomprehensible to most users. So let's see if a simple visualization of the corresponding policy graph might be more helpful. As you can see, it is still very hard to make sense of what exactly is going on from such a graph. And if you were a user of a travel planning system that in fact returned such graphs whenever you ask for a policy, that might not be very helpful to you. Now the question is, what can we do about this? One strategy studied in previous literature looks at constraining the structure of the solution so that the system always produces simpler solutions, but this may not always be feasible. A more useful option may be to consider summarization strategies, though most existing one either only considers just state abstraction or highlighting actions in a set of representative states. In real life, we are more likely to refer to subgoals while summarizing our own strategies. For example, in the case of traveling to the airport, you might say that you would want to first get to the shuttle stop, then to the terminal, then to the gate, and so on. And this is going to be the strategy we will also be employing in this work. Now the challenge here is the question and the challenge is how to extract such temporal abstraction directly from the given policy and the original problem when they may not be specified in such manner. We will specifically address this challenge by leveraging the idea of landmarks from classical planning literature, where they have been defined as facts and formulas and their relative ordering that needs to be satisfied by every valid plan in the given domain. In the slides, you can see an example of a simple domain, their possible plans, and the landmarks that correspond to that domain. To extend the ideas to stochastic setting, we first need to define landmarks over execution sequences that leads to goals instead of over plans. Since we are interested in policy summaries, we further restrict the execution sequences to just the ones feasible under the given policy. On the right, you can see a simple policy highlighted in bold edges and the landmarks that correspond to that policy. It's also important to note that policy landmarks are guaranteed to be a superset of model landmarks, which may consider all possible execution traces and not just the ones that correspond to the given policy. Now, the obvious next question is, how do we calculate it? Here, we can leverage the methods developed in classical planning to generate such landmarks. The easiest method would be to consider a model constraint to only allow the policy actions, and then consider its all outcome determinization, and then use standard classical planning method to generate landmarks from this deterministic model. And the landmarks generated from this model would correspond to policy landmarks. Now, since this model is only meant to generate landmarks, and most popular methods for landmark generation consider delete relaxations of the model, we can actually get by considering even simpler models. In fact, we can consider a model where there contains one action for each policy step, and the output or the add effects of that action would correspond to a union of all possible stochastic effects of the corresponding action in the original model. Here you can see a simple example defined for such a compilation over the example travel domain. Now, going back to our travel domain, here is a simple summary that we created for the original policy that we had visualized as the policy graph. And you can see that here the summary consists of the various subgoals of the form. First, the policy first requires you to get to your garage, then to the bus stop, then to the station, then to airport, and so on. In terms of evaluating our method, the first thing we were interested in was how our system performed on standard stochastic domains, and whether in fact the summaries generated on these domains are much simpler than the ones than the entire policy for that domain, and also whether considering policy landmarks as opposed to just model landmarks does give us additional information that were not part of model landmarks. In fact, for the domains we tested, we did see that both were the case, as in like our summaries were much smaller than the reachable states under the policy, and the policy landmarks did contain additional information. In terms of user studies, we wanted to test whether landmarks make meaningful summaries, at least to people, when they're generating summaries. To test this, we described policies to users and asked them to summarize and see if they would in fact choose landmark facts as part of the summary. So we ran this study on Amazon Mechanical Turk, where we had nearly 60 participants, and they were shown policies from 2 different domains and asked to summarize by selecting subgoals that they thought were important. And we did find from the results that people do tend to select landmark facts by an overwhelming percentage. Now, now that we have a system that can generate subgoals, that captures regularities among the various contingencies, the question is, where do we go next? So one open challenge is that there still could be a large number of subgoals. To consider an extreme edge case, consider a domain that is completely deterministic. Now the policy landmark would constitute of every state in the execution trace of that sequential plan. The problem here is that we are currently not differentiating between landmarks that might be of higher value to user than others. This speaks for the need to leverage state abstraction techniques along with these techniques that are meant to extract subgoals. And one of the questions related to that is, how do we differentiate between subgoals that are of higher value to users than ones that are not? Another open challenge is, how do we operationalize this summary into an interface where they can use such subgoals, generated subgoals, to actually focus on different parts of the policy, or use these subgoals as a way for the user to ask questions about alternate policy they would have liked to see, and use that as a way to perform explanatory dialogue. And these are some of the things we are looking at going forward. Thank you.